Greetings everyone. Today we have gathered here to discuss our final year project, Hybrid Deep Learning Framework for Financial Market Prediction. Financial markets enable the buying and selling of assets such as stocks, bonds, and derivatives to support investment and risk management. Trading activities have increased significantly due to globalization and digital platforms. Option trading is an important form of derivative trading, widely used by individual traders and financial institutions. An option is a financial contract that gives the holder the right but not the obligation to buy or sell an underlying asset at a predetermined price within a specific time period. Option trading allows participants to gain exposure to price movements without owning the actual asset. There are two main types of options: call option for buying and put option for selling the underlying asset. Options are commonly used for hedging risk, speculation, and improving portfolio performance. The pricing of option is a critical task as it directly affects profitability and risk exposure. Mathematical models are traditionally used to calculate the fair value of options. With growing market uncertainty and rapid price fluctuation, accurate option pricing has become more complex. This has increased the importance of improving existing pricing techniques. Options are used to reduce risk, make profit, and improve results. So, pricing them accurately and correctly is very important. Because market changes very quickly and is always uncertain, traditional mathematical models are not always accurate, so better pricing methods are needed. The Black-Scholes model is a mathematical formula used to calculate the price of options. It works by using factors like stock price, strike price, interest rate, and volatility to estimate a fair option, always assuming the market behaves smoothly. But in reality, the market never behaves smoothly. So, coming to our problem statement, in real world scenario, many stock market traders use multiple models to predict their trades. BSM is one of the widely used models by many stock market traders. Option pricing trades use BSM to predict the option prices. But BSM has many disadvantages. It often fails in high stress market conditions. It is trained with a mathematical formula that only works for a standard market. It fails to predict volatile markets. The other major disadvantage include it assumes constant volatility. Assumes market risk stays the same over time, but in reality, volatility frequently rise and falls. Another disadvantage include log normal returns. It assumes asset price change smoothly without sudden jumps, which ignores crashes and spikes. Another disadvantage is no transaction cost. It assumes trading is free, but real market have fees, spread, and liquidity cost. Another disadvantage includes continuous trading fix. Assume you can trade every microsecond. So, the abstract of a project is the traditional option pricing model, such as Black-Scholes Merton, rely on assumptions of constant volatility and ideal market condition, which can result in pricing inaccuracies during periods of heightened market turbulence. To address these shortcomings, this project introduces a neuro-symbolic hybrid option pricing system that integrates principles of mathematical finance with deep learning techniques. The framework is structured in three interconnected components. First, a variational encoder, VAE, is employed to capture and estimate latent volatility regimes. Second, a physics-informed neural network, PIN, incorporates the Black-Scholes partial differential equation to maintain financial consistency and enforce no arbitrage condition. And third, a residual learning module refines pricing outputs by incorporating real-time market frictions, including liquidity effects and bid-ask spreads. By merging established financial theory with adaptive AI-driven modeling, the proposed approach enhances pricing accuracy, robustness, and interpretability in evolving market environments. So, the need and motivation for the project is increasing market volatility demands more robust and adaptive option pricing methods. Existing mathematical models alone are inefficient for handling complex market behavior. Advances in artificial intelligence enable the analysis of large volumes of financial data. Machine learning models can capture nonlinear patterns ignored by traditional approaches. However, financial applications require transparency and explainability. Combining mathematical finance with AI can balance accuracy and interpretability. A hybrid pricing framework can improve decision making under uncertain conditions. This project aims to develop a system that produces reliable prices along with clear explanations. So the basic concepts that have been used in our projects are financial markets, a platform for trading financial assets, derivatives, instruments whose value depend on underlying asset options. These are rights, not obligation to buy or sell at a fixed price, option pricing, estimating fair value using models, Black-Scholes model, a mathematical model for European options, volatility, a degree of price fluctuations, risk-free rate, written with zero risk. Example, government bonds, strike price, agreed price in option contract, time to maturity, time until option expiry, implied volatility, markets accept expectations of future volatility, volatility smile, variation of implied volatility across strikes, machine learning learns pattern from financial data, deep learning captures complex and nonlinear relationships, neurosymbolic approach combines financial theory and AI, residual learning corrects models error using real data. So coming to the literature survey, the base paper that has been chosen for our project is predicting option prices from Black-Scholes model to machine learning models. The key features include compares Black-Scholes model with ANN using 33,000 plus real options data. The pros include ML model captures nonlinear patterns and improve accuracy, but the cons include black box nature, needs quality data. The next paper, a novel market sentiment analysis model for forecasting stock and cryptocurrency returns. The key features include it uses option implied sentiment to forecast stock and crypto returns. Pros include a strong predictive power and profitable at longer horizons. The cons include short time period and uses very complex indicators. The next paper, Black-Scholes equations in quantitative finance with variable parameters. The key features include generalized Black-Scholes with time-varying parameters and quantum approach. The pros includes more realistic pricing and it is very theoretically robust. The cons include it is theoretical, limited real-world validation. The next paper, dynamics among the term spread, stock market volatility, forecast, financial market risk, and oil price. The key features include ARDL analysis of monthly US data on volatility, term spread, risk, and oil. The pros include identifies long run links useful for risk insights.
The next paper, which is ML Stock Market Forecasting and Market Efficiency, a comparative study. The key features include comparison of 7 ML models across 55 markets from the time duration of 2011 to 2022. The pros include large data set and it shows link between efficiency and accuracy. The cons include no single model is best for all the markets. The next paper, a hybrid relational approach towards stock price prediction and profitability. The key feature is that it combines relational features, which is RF2P and TCLM for cross market prediction. The pros are improving accuracy and real world profitability. The cons include relational features, which adds more complexity. The next paper, ST Trader, a spatial temporal deep neural network for modeling stock market movement. The key features include a combination of VAE, GCN, and LSTM on minute level US stock data. The pros include capturing spatial dependencies and superior forecasting. The cons include it needs large data for processing and it is computationally costly. Next paper, a novel and effective method for quantifying the performance of time series volatility. The feature includes proposal of CWF distance method for volatility quantification. The pros are detects abnormal changes better and it is robust and interpretable. The cons are it uses new method and it needs more validation. The next paper, Pleno Alignment Framework for Stock Trend Prediction. The key feature is that it uses multimodal framework using prices and social media text. The pros are that it handles sentiment well and it performs better with MCC and higher accuracy. The cons include that it requires text data and it is highly computational dataset.
The issues and challenges of the project include traditional option pricing models are based on simplified assumption that rarely match real market condition. Volatility in financial market is dynamic and change suddenly due to economic events. Transaction cost. So the So transaction cost, that is the fees or charge paid when buying or selling options which reduce the profit. Bid ask spread, the difference between buying and selling price of an option causing extra cost to traders. Liquidity issues, when there are not enough buyers or sellers, making it hard to trade at the desired price. So these are all the reasons why we say the option prices are always changing consistently, and the traditional models cannot predict them. So the classical models fail to account for these real constraints. As a result, option may be underpriced or overpriced during high stress market. So ML models can improve accuracy, but often treated as black box system. So as a result, the options are always underpriced or overpriced during a high stress market conditions.
A definitive conclusion from all the study in previous includes a conclusion of ML models outperform traditional ones but need more data and tuning. Hybrid models, which is theory plus ML, are most promising. Market efficiency limits predictability. Behavioral and macro features are critical, and simpler models still competitive in some cases.
Fine. For the proposed work, we propose a neurosymbolic hybrid architecture that decomposes option pricing into three distinct computational stages. Unlike traditional black box AI, this system uses the Black-Scholes partial differential equation as a central constant. Next slide, please. So, for our architecture, we'll be using three different layers. For the layer one, you'll be using variational autoencoder. So, using this variational autoencoder, we'll be solving the constant volatility on the log normal forms. So, instead of using fixed volatility, the variational autoencoder looks at raw market patterns and maps them to a latent space. This space captures fat tails and volatility skew. The variational autoencoder are then decoded outputs a dynamic time varying volatility. For layer 2, we'll be using physics informed neural networks, where it is used to solve the mathematical inconsistency and hallucinations. It uses physics informed neural network to solve Black-Scholes partial differential equation. The AI is not allowed to just guess a price. Its loss function includes penalty. The price violates the PSM law. For the layer 3, we'll be using residual frictional correction, where it solves the feed forward neural network. It solves liquidity friction and discrete trading. This layer also looks at the bid ask spread and volume and calculates residual correction. It adds the real world cost to the theoretical price and gives the final price. That's it.
The system requirements and tools involved in this project are the CPU component, which is a specification of Intel Core i9 14900K, the GPU, which is NVIDIA RTX 4080. We specifically chosen this GPU because it supports deep learning super sampling, which is superly important to support the deep learning algorithms involved in our project. The RAM is a normal 64 GB drive, the storage is 1 terabyte, and the network is 1 Gbps, which is mostly our hi-fi bandwidth. The front end involves React JS with Tailwind CSS, which usually imports the React components and use the CSS charts and read charts to help in the visualization of the charts involved in our financial market system. The AI and analytics module involves Gemini 3 Flash API, which allows to access the real-time data of the stock values. The TensorFlow, it is used to run the client side AI model execution. The TypeScript based Black-Scholes modern model, it helps to design the mathematical formulas and statistical regulations. The math engine such as Mac.js or JPU.js helps to keep the Black-Scholes model formula and other statistical formulas involved in that in a separate module, so that it is not being hacked, or it's just kept safe. So the modules involve physics involved informed neural network. The first module here, the purpose is to ensure predictions and to obey financial laws. The core idea behind this module is to embed the Black-Scholes PDE into training. Instead of purely fitting the data, we add the physics-based loss using a loss function. Why this matters that it because it prevents the nonsensical outputs, it improves generalization outside training data, and this is the symbolic backbone of our system. The next module is the variational autoencoder, which is the latent volatility modeling. The purpose of this model is to hide the volatility regimes instead of assuming a scalar product. Why we chose this model? Because volatility is non-observable, which is latent, and it is non-stationary, and it is also multimodal, which helps us to predict the calm versus crisis situation in the stock market analysis. What it does is that it encodes market features into a latent space and it learns the distribution using some graphical values. The output involves a probabilistic representation of volatility regimes. The effect is to capture regime shift early, and it also handles fat tail behavior better than constant volatility. The next module is the residual learning block market. Its purpose is to bring and bridge gap between theoretical price and tradable price. The input includes the output from PIN model and then the limit order book data. It involves terms such as bid ask spread, volume, and liquidity depth. The model assumes a mathematical formula to assume the P final price. What it learns is that the liquidity premium, the slippage effects, and the execution constraints. This is effectively a calibration layer using real time microstructured data. Some of the key innovations include decoupled learning, where we separate the volatility estimation, pricing, and market correction, which results in reducing the complexity per module. Then we also compute the neuro plus symbolic fusion, where the neural networks learn the pattern extraction and the PDE will learn the hard constraints, such that it avoids pure black box behavior. The regime aware pricing, it uses VAE so that the pricing adapts dynamically to volatility regimes. So we have attached the screenshots of our output screening.
So, so here, as you can see, is the dashboard of a project where it just tells us who we are and why we're doing it, along with other technological explanation. As we move on to our next screen, um, here we can see at the top, these are the recommended signals given by our AI and the BSM engine. So once we selected it, next screen, it tells us what is the current price of it and what is the fair value, which means at what price it is being traded at. And if you take this call option, how much profit you'll be getting, or if it goes south, how much loss you'll be losing, etc. And if you're not convinced by the call call signals given by the AI, you can also manually select your own spot price, strike price, etc. as shown on the left. And that's it.
So now we'll move on to the real live demonstration of our project.
Thank you.